In this video, we're quickly deriving the change of base formula for logarithms. So if we have a log with base b of a, we can change that in terms of any base that we want by taking this log base c, that's our new base, of the original argument a divided by log base c of the original base b. Now, like anything with logarithms, if you want to prove the properties of logarithms, you always go back to expressing them in terms of exponentials. And the key to that is to give the expression a name. So I'm going to call it y. I'm going to write y equals log base b of a. Now we use the definition of logs to write this in terms of exponentials. That statement is totally equivalent to b to the y equals a. Now all I have to do is take the log base c of both sides. So log base c of b to the y is equal to log base c of a. Next, I use a property of logarithms that the log of something to a power is the same as bringing that power out in front as a multiple. So I have y log base c of b is equal to log base c of a. And finally, we divide by log base c of b, and we have what we were after. Y is equal to log base c of a over log base c of b. And remember that y was the name for the original expression, log base b of a. So I get that log base b of a is log base c of a over log base c of b. Next, we're going to look at a couple quick examples, and the first one answers the question of why should we care? We're asked to write log 2, in other words, the common log of 2, in other words, the base 10 log of 2, in terms of natural logs. And the reason we care about reformulating this in terms of natural logs is that a lot of technology, including calculators and computer algebra systems, can't deal with logarithms other than a base of e, in other words, a natural log. So there are a lot of technologies out there where if you see a log with a base other than e, you're going to have to use the change of base formula on your own. To emphasize what the common log is, I'm going to write log base 10 of 2. And then we use the change of base formula, which allows us to change to any base we want. In this case, we're choosing e. So I write log base e of 2 over log base e of 10. And of course, log base e is really just the natural log. So I have natural log 2 over natural log 10. In the second example, we discover an interesting formula that's actually true in general of logarithms. We're asked to write log base 2 of 5 in terms of base 5 logs. Note that the base we're converting to is the same as the original argument of our log function, and an interesting formula pops out of this. So I'm going to apply my change of base formula. Log base 2 of 5 is the same as log base 5 of 5. We're changing to a base of 5 over log base 5 of 2. Then we apply the property that log base 5 of 5 should be equal to 1. Anytime the base is equal to the argument, you just get 1. And I end up with 1 over log base 5 of 2. So look at the relationship there. I swapped the argument of the log function and the base of the log function. And those two things are related by a reciprocal. So it would be interesting to show that this is true in general. And all we have to do is generalize to just writing log base b of a. And if I convert that to a base of a, I would have log base a of a over log base a of b, and log base a of a is just 1. And so it turns out in general, if you swap the base of a logarithm and the argument of a logarithm, those two expressions are related by a reciprocal. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.